Well, hey, pre-calc, you know the drill here. It's the do now. Go ahead and hit pause on the video till you got your own answer worked out. Hey, well, that was really quick. So there's two steps in the algebra problem. Subtract 7, divide by 4. Leave your answer in fractional form or not. I left it as a fraction. You don't have to. We're looking at logarithms today. Solving logarithmic equations. Our learning target, same as it was yesterday, we'll be able to solve logarithmic equations. So we have this list of strategies. We're not going to make any changes to it today. We've seen this before. No new strategies, just continue to use the same ones. We'll see maybe a couple of different applications of these same ideas. So 2 examples. Here's the first one. Anytime you have in your equation a log such as this one, which is part of like an algebra equation with the coefficient of 4, and we got the plus 7 over there, we're going to want to isolate the log as our first set of steps. Okay, so the same steps we just saw in the do now, we're going to subtract 4. All right, 2 examples today. Here is the first of them. Anytime you have an equation, you've got a logarithm in here, and we've got some other numbers going on. We've got a coefficient of 4 and that constant of 7. Isolate the log. That'll be our first step, or several steps. Isolate the logarithm. So in this case, it's the exact same problem we just saw in the do now. So we're going to go ahead and do those same 2 steps, subtracting 7. And, oops, let's get a different color. And then we'll divide by 4. Resulting in log base 5 of x equals, and again, leave this in fractional form or change it to decimal. Either way, once we get to this point, so we've got 2 options. I will not demonstrate both of them, but the 2 options are, you could either change this logarithmic equation into exponential form, base of 5 raised to the power of 11/4 equals x. That's option 1. Or we could do the inverse property. So we could raise both sides to as the exponent on a 5. 5 to the power of log base 5 of x equals 5 to the power of 11/4. Okay, and then 5 to the power of log base 5, those are inverses. They're going to cancel, and we'll be left with this x equals 5 to the power of 11/4. All right, now some of you might have been thinking on your own here, instead of doing the inverse property as our last step, if we had just rewritten that log equation in purple into exponential form, this is exactly the same thing we would get. 5 is the base. So 5 is our base to the power of 11/4 right there. And then it's going to equal this output of x. So we're going to get the exact same thing. It's a matter of whether we do the inverse property to get there or whether we just rewrite it as a as an exponent. I'm going to try to find my calculator so that I can actually find out what 5 to the power of 11/4 is. I cannot do that in my head. 5 raised to the power of 11/4. So we're going to have final answer right here is approximately equal to 83. I'm going to go to 4 decimal places. 5925. All right, second example of 2. So this one, we've got a log on each side of the equal signs. So first of all, make sure we have the same base, because if we don't, this is going to change things, how we approach this. So log base 6 of negative 7x equal to log base 6 of 13. Since they both have log base 6, I can use the inverse property. It'll be the same inverse property on both sides of the equal sign. My other option that I sometimes do of rewriting this log in exponential form is not going to work, because it's not very nicely. I mean, I could do it. It's just not it's not a nice option, because I could have a base of 6, but then I got this whole thing as the exponent. It'll simplify. It's not a whole lot of not a lot of extra work, but let's just stick with one option. So 6 will be the base of my exponent on each side of the equal sign. That's going to be my exponent on the left side. That's going to be the exponent on the right side. Inverses, log base 6, 6 to the power of, those are going to undo one another. Same happens on the other side. So negative 7x equals 13. And our remaining step is solve for x. So we'll divide both sides by negative 7. So final answer is negative 13/7, or if you want to do this as a fraction, 1.8571. Let me double check. Calculator. Yep, nice. All right. There is a couple of other options that we could do, and this is the fastest. Okay. Sometimes when you're dealing with a problem, you got an equation, you're like, I could do it this way, I could do it that way, I could think of some different options, and we don't know which one will be best. Well, yeah, that's going to happen. Sometimes you just don't know which is the best option, and so you pick one and you do it, and then you learn from it. And maybe next time you're like, that was pretty long, I should do it a different way. And maybe it worked out great. So a different option, so we could rewrite this in exponential form. I started doing this last time, and I wanted to do the short way first, so we did that. We can write this in exponential form. You could pick either side to start from. I'm going to start from the left-hand side. So this is my base. That whole thing right there is going to be my exponent. Equals. And then here is, whoops, here's the output. Here's the output. Computer lag. Output. So that's going to be on the other side of the equal sign. And then once again, so here, what have I just done? So this one was, sorry, I got to label both sides. Here was my work. So the first one, I used the inverse property. This time I'm going to rewrite as an exponent, right as exponential form. Okay, so I still get to use the inverse property now, because 6 to the power of is the inverse operation of log base 6. And so those are going to cancel. I'll be left just with the 13. So I'm still going to end up at the same result here. 13 equals negative 7x. Divide both sides to get x by itself. And I'm going to get the exact same answer. And it's actually about the same amount of work. So I forgot a negative sign last time. Man, I'm going to be more careful. Okay, option 3. We rarely get 3 options, but I'm going to go ahead and do the third option here. Is the longest of all of them. Those first 2 were about the same length. So here's another approach, which has some cool tricks in it. It's a little bit maybe more sophisticated, but also longer. Sophisticated does not always mean longer, but in this case, it is going to be longer. So one of the things we often do in math when we're solving an equation is we want to bring everything to one side of the equal sign and set it equal to 0. And instead is our third option here. So I'm going to just subtract log base 6 of 13. We'll do the same on both sides. So those are going to subtract to give me 0. So we're going to have log base 6 of negative 7x minus log base 6 of 13 equals 0 on the right-hand side. And then, so I have two different logs that are being subtracted. I can condense that, take this subtraction, and I'm going to rewrite that as a single log containing division. Log base 6, negative 7x divide by 13. Okay, so I got a single log. That's nice. Hooray! And then at this point, I will again change this log into exponent form. Let me write down what I've done here so far. So bring all terms to one side. Next, we condensed that log. Probably don't need a D on that. Next, I am going to change this into exponent form. Okay, here goes. Change to exponent form. So 6, exponent of 0. Inside the parentheses is my output, negative 7x over 13. All right, so hold on one second. Anything raised to the power of 0 always equals 1, whether it's written in exponential form or in log form. We could have actually recognized that right there. Anytime a log with any base, with any output, doesn't make any difference. Any log that equals 0 has an answer of 1. So get the pen ready. Here, all right, so 6 to the power of 0, that is 1. So I'm just going to change it to 1. I've evaluated it. Type into your calculator, 6 to the power of 0. It's 1. And then negative 7x over 13. We could have, if we'd really been paying attention, we could have noticed that the green step there, when log base 6 of negative 7x over 13 equals 0, we got the 1 right there. And so we could, at that point, skip the blue step and just say, look, that output, negative 7x, that equals 1. And we could have skipped the blue step and gone straight to the purple if we recognize that as a property of logs. Property of logs. Okay, any log which equals 0 has an answer of 1, right? So just take the output, make it equal to 1. Or if we don't notice it in the log form, then we got it here in exponent form. It's a property of exponents. Whatever base you've got, raised to the power of 0 equals 1. Okay, let's continue. We're going to solve for x. So I'm going to multiply both sides by 13. So I'm going to get 13 equals negative 7x divided by 7. Sorry, by negative 7. And final answer, negative fraction, negative 13/7, which still gives me that same decimal approximation. Okay. So the moral of the story really is not, hey, you should do the problem this way versus that way. The moral of the story is there's multiple approaches that will all work. Sometimes they're a little bit longer. Sometimes they're a little bit shorter. And really the only way we're going to know which one is shorter, which one is longer, is by doing them a lot as we gain that experience. And then next time we'll know better.